Hello everyone, I am Kaushik Shankarar and this is my ID card. And the date is 2/8/2024 and the video is about the demonstration of experiment of week 3 on the course Electronics Lab. The objective of this experiment is to read the datasheet of an IC, in this case 74LS163, which is a counter IC, and also to configure the IC to achieve a certain functionality. Let us read the datasheet first. This is the datasheet for 74LS163 and this is the pin diagram of that IC. The VCC and ground must be connected to the power source as seen in the experiment of week 1. I do not know what other pins are, so let us proceed to the next page. And here is the diagram for 74LS163. It seems that CLR, load, ENT, ENP, CLK, A, B, C, D are all inputs and RCO, QA, QB, QC and QD are outputs. I have searched on the internet and got to know about the pin CLK, which is clock. A clock signal is a square wave which is used to synchronizing electronic devices. By reading this paragraph, I got to know about RCO, which is ripple carry output. It is used for cascading more than one of these ICs to have a larger bit count. It is like ripple carry adder. This page contains the signal diagrams for the IC and take look at this area. When the clock goes high here, all the bits changes to 0. QA, QB, QC, QD all are 0, which represents the binary number 0. And on the next clock rising edge of the clock, the QA turns 1 and all other outputs remain 0, which is binary equivalent of 1. On the next rising edge of the clock, the QA turns 0 and the QB turns 1, which is the binary value for 2. Like this, on 12, the QA is 0, QB is 0, QC and QD are 1 respectively. This is also, as mentioned here, binary equivalent of 12. So, in every rising edge of the clock, the counter counts plus 1. This is the circuit I have built for this IC to count from 0 to 15. The VCC and ground are connected to the 5 volt and ground on the ADALM kit, and the RCO, QA, QB, QC are connected to an LED which is connected to a 330 ohms to limit the current. This is done in order to observe the output. CLR, load, ENT, ENP are connected to VCC as I searched for it. It seems the load is used to for loading A, B, C, D inputs to the output, which we will see later on this video. And ENT and ENP are used for cascading. The clear CLR pin is used for clearing or resetting the IC. The CLK clock pin is used to provide the clock input. As you can see here, I have already built the circuit. This is the IC and these are all the LEDs connected to the 330 ohms resistor. And for the clock input, I am using a button because it will be easier to see how the IC is working. You can see that after giving a pulse, the counter adds a 1 and displays 1 in binary. Like this, it counts up to 15 and on the 15 the RCO turns high as it would be useful to ripple carry the output. Now, as in the problem, we also have to count down from 15 to 0. I am going to use 74LS04 IC, which is a NOT gate or inverter. It is done because while inverting, the counting seems to be counting down rather counting up. I am going to give the output of this counter to the 74LS04 IC and the output from this IC to the LED. I have finished building the circuit with the output goes to the inverter and then to the LED. As you can see, the initial value is 15 rather 0 because without the ripple carry being high, because it is the zeroth state from the counter IC, but after feeding through the NOT gate it becomes as 15. So while pressing the button it goes down from 15 to 0. As you can see, like it happened on the 15th here, the 0 makes the ripple carry high. I have disconnected the inverter from the circuit and I am going to explain how the load functionality works in the IC. To explain how the load works, I have connected a button which is an active low in this case by providing a resistor across it. It acts like a pull down resistor in this case. I have set the inputs A to B as the number 8. So when I press the load and generate a clock, it simply outputs what on the inputs A, B, C and D. In this case, it is 15. After loading the data from the inputs, if we count further, it counts from the number which we have loaded. Now I have removed all the components like the LED and the button and simply connected the channel A of the ADALM kit to the clock and the channel B to observe the outputs. As you can see in the Pixel Pulse software, the clock is set to 100 Hz. This is the output of QB. This is the output of QC and this is the output of QD. Hello, I am back on 6th August 2024 after attending the live session and got to know about we should add this 40106 IC between the input clock signal and the clock input on the 74163 IC. As ADLM kit cannot drive more current, the output shown on that day was glitched and not as perfect as we seen on the datasheet. So let us see the output now. Now I am going to start the ADLM kit and generate a square wave on channel A with 5 volts as peak. And the frequency as 100 Hz. You can see that now the clock is counting automatically by using the clock input from the ADLM kit rather than using a button as clock input, which we have done previously. Now, while probing the outputs with the channel B, we can see that it is very clean and similar to the signal we have seen in the datasheet. This is for the QA. This is for the QB. QA and QBs with this almost equal, as both of them will be turned high from a rising edge to another rising edge. This is the output of Q3. You can observe that it is the width of the pulse is slightly larger, as the third bit will not turn high as frequent as first and second bits. This is the output of Q4, which will turn on much slower in frequency than other pins. This circuit can be used to analyze any logic circuits with 4 inputs, as it would be easier to generate a truth table of any logic circuit with this counter IC. Thank you.